Calculus, in our optimization thinking, some common examples that come to mind are optimizing things in geometry, optimizing things as far as business and economics goes, and we looked at both of those yesterday. And we're going to look at something that involves distances today, and those would be common examples in grade 12 calculus. So we have a lighthouse problem, and it's located on a small island 4 kilometers west of point A on a straight north-south coastline. Of course, everything's perfectly north-south in a math classroom. And we're laying power cable from point B on the shoreline 12 kilometers north of point A. So we have all of this detail, and we want to be able to come up with a diagram that's helpful. So we have this situation where we've got A and B, and we have L for a lighthouse, and we want to minimize the cost. Big idea. Okay. We want to get the power from point B to L in the cheapest way possible. So are we going to run it down the shoreline and straight across, or are we going to run it kitty corner like a hypotenuse, or are we going to do it somewhere in the middle? So the question is worded to give you a hint that possibly the best situation is to run the cable down a ways to point C and then run it through the water there. But we don't really know what the cheapest would be. Would it be to run it straight down and then straight over? Would it be cheapest to run it kitty corner like that? Or would it in fact be cheapest somewhere in the middle? And so that's what we're determining today. If I want to effectively optimize something, I need to make sure that I consider my endpoints which my endpoints would be straight down and straight over, or kitty corner. And I'm going to consider my extrema. Oops, I hope I could spell. So mathematically speaking, if I want to optimize something, I need to think about these two things. All right, let's set the problem up. Let's assume that it would be good to have C located some unknown distance from A, X kilometers north. That means from B to C, I would have 12 subtract X kilometers. I could use Pythagorean theorem to find this length. It would be the square root of 4 squared plus X squared. So I have determined one variable that can represent all the possible scenarios. So let X represent, I'm really struggling with spelling today, represent the distance of cable how do I word this here? You know what, I can word this a little bit better if I say let 12 minus X. Let 12 minus X represent the distance of cable on shore. Does that make sense? That first little section right here, that would be the distance of the cable on the shore. And then this would be the distance of the cable underwater. Okay. I want to have my minimum cost. So I need an equation that represents cost, since that is what I'm trying to find. So my cost equation, or minimize in fact, cost equation would be the cost in terms of X will be, I have how many dollars on land? $2,000 a kilometer? $2,000 a kilometer on land, so that would be $2,000 times 12 subtract X, plus I have $6,000 for every distance, I'm just checking my number, every kilometer underwater, which in this case is square root of 16 plus X squared. And that is what I'm trying to minimize. So if I want to minimize Number one, I want to look at my endpoints. What values make sense for x? Well, if x were 0, so if this guy were 0, that's the situation when I run the pipe all the way down to A and then all the way over. So that would be one of the endpoints for x. If x were 12, that's where this is 0. That's the situation when I have a direct line through the water. That's the other endpoint. So x can lie between 0 and 12. It wouldn't make any sense for it to be greater than 12 or less than 0. So I'm going to look at my function at those two places. Maybe that in fact is cheaper than laying it halfway down the shoreline. So if I put those values in, I get $48,000. So that's straight down and straight over. The second one is where you run it totally in the water, which in fact is way more expensive, $75,894.70. If you want to minimize, you need to consider also your extrema, which is where your first derivative equals 0. Maybe that's the minimum cost. So let's look at our function and determine its derivative. It can be helpful to perhaps tidy up our function a little bit. I have 24,000 subtract 2,000x plus 6,000 times 16 plus x squared to the 1/2 because I like my powers. My derivative would be 0 subtract 2,000 plus, bring down the exponent, reduce it by 1. Don't forget the guts. I'm going to tidy it up just a little bit. Okay, so I have 6,000x on the top, and this guy is on the bottom. All right, it looks better. For my extrema, I set my derivative equal to 0 and find possible maximum or minimum values there. Okay. I'm going to add 2,000 to both sides. I am going to multiply both sides by 16, root 16 plus x squared. Also divide both sides by 2,000. I am going to square both sides. I am going to subtract x squared. X is the positive and negative square root of 2. Negative root 2 is not in the interval. That would be taking it further down the shoreline, which is not what we're considering for this particular one, and would likely not be cheaper anyways. Let's look at our function at the value root 2 and see if it is in fact a minimum or if we're going with one of our endpoints. Sorry, I should call that C. Okay, so if I type in root 2 into the original function, and again, you're trusting my math on this, I have $46,627. So this one is effectively the minimum value, not a lot less than one of the endpoints. Where are my endpoints? But a little bit smaller than both. So that is the best place to put our cable. Therefore, the minimum cost will be $46,627 when point C is located root 2 units from A.